Let's see how this goes. Okay, so we're trying higher resolution to see if we can get cameras to work better. Focusing in on Chem 124 questions, we have the second half of Homework 6 quiz today. We just did question 11. Should we do question 11 again just so people can see it? It's only this one you and I were working on yesterday as well. Let's go ahead and take a look at it. So, yeah, you see how the frame rate is kind of like, it's a little jumpy. We'll see how it goes. That's part of the problem. I mean, it's mostly okay, but we'll see how it goes. So this problem is asking us to look at the reaction of sodium carbonate with acetic acid. And remember, there's a lot of different ways that you can write acetic acid. I write it this way because I like to accentuate the fact that there's a functional group here. That's the carboxylic functional group. This is going to react to produce sodium acetate, CO2 gas, and H2O water. Normally we wouldn't write it this way, but I didn't give myself enough space at the end of the board. And it's also going to turn out that in this problem, the products don't really matter, right? So that allows us to balance the chemical reaction. We're going to have a 2 here for the acetic acid, a 2 here for the sodium acetate. And the question is saying we've got 100 grams of this. We've got a 0.054 molarity solution of this. And it wants to know what volume we need. So it says in the problem that we specifically want the amount to completely react. So the amount to completely react is essentially saying when we get to this end step, I have 0 left over for both things, because that's the complete reaction, right? So that becomes the kind of important conceptual step. There are 3 important conceptual steps. One is writing the chemical reaction and balancing it. The other is realizing that at the end of the reaction, I want nothing left over. I've got 0 excess. And then the third important conceptual step is knowing how to get from our starting materials to moles. So if we have a molarity, it's molarity times volume gives us moles. And if we've got a grams, it's grams divided by molecular weight gives us moles. Right? We need those 2 things in order to get to our starting point. Remember, we always have to start in moles. Now, the reaction, since both things are going to be 0 at the end, both things are limiting, we could really do this equation either way. Because what we're really saying in this step is that 100 divided by 106, well, let's do it this way. Let's do the conceptual work again. What we're saying in order to get this to be true is that the moles of Na2CO3 are equal to the moles of CH3COOH. But in order to make it so that I can actually have an equality here, I need to multiply by 1 mole Na2CO3 for every 2 moles CH3COOH. Right? This allows me now to notice that I'm going to cancel out my moles of acetic acid. Now I'm saying my moles of carbonate are equal to my moles of carbonate. Right? That's the other important step that we kind of did in the chemical reaction in balancing the chemical reaction. Now I can plug in my information. I'm going to have 100 over 106 is equal to 0.054 V divided by 2. And of course you can all solve that equation. Right? Once we set up the algebraic expression, the problem is easy. But setting this up, the amount of conceptual work, the amount of thinking about chemistry we have to do to get to that point, that's the interesting part of the problem. Okay. 100 divided by 106 is going to be like 0.95. Multiply that by 2, you've got 1.9 divided by 0.054. I can't do that in my head.
So similar to this problem for 21, it's kind of just a straight geometry problem actually. It's just saying how many moles of excess reactant are present when 500 milliliters of.
Well, hold on. So are we ready to move on to that
I
problem?
just have a question about it because
Yeah.
all we get are the reactants. So how do we know what the mole ratio should be?
Ooh. You're given what the reactants are as well, right?
Yeah, we're just given like sodium hydroxide reacts with sulfuric acid. So should we just look at those and like
So remember, we spend a lot of time balancing chemical equations and predicting products, right? That was the whole types of reactions lab, and we did a worksheet associated with that. So yeah, we should be able to look at this problem. Is it okay if I move on then? Okay.
It was only like 35,000-ish milliliters.
No idea.
What number is it?
Number 11, like 3.5 liters. 100 grams is quite a bit, and the concentration is pretty low.
Yeah,
So like 3.5 liters.
Like 34,000.
Yeah.
I got.
Oh, 34 liters?
Yeah.
Because if it's 34,000, not 3,400, 34,000.
I don't remember what it was. I got that, something like that.
It's
So
like-
when I didn't do it this way, I did it a
It's like
different way.
34.9 liters.
Yeah. Mhm.
So I
Wow.
just rounded to 35.
Well, so if we think about this, this is about a mole, right?
Yeah.
This is approximately a mole. How many times am I going to need 0.054 to get 1 mole? A lot. Because we've got such a low molarity. Honestly, my guess is this problem meant to have 0.54 molarity. And there was a typo either when the problem was put into the book or when I copied the problem from the book. There was a typo someplace and it made it so it's 0.054. So you're going to have 10, 100. Yeah, you're gonna have to have like 20 or 30 liters, right?
Yeah.
Because if I had 10 liters, that would be 0.54 moles. If I had 20 liters, that should be about 1 mole. So it's going to take a lot. And then it's a 2-to-1 ratio, so then you're going to double that, and it's going to be like 40 liters. Someplace between 30 and 40 liters. Again, because this concentration is so low.
I was a little spooked when I saw
Yeah,
35,000.
still. So if you were doing this titration, remember in lab where we had to pick how much solid we used? This is why we don't use 100 grams. And we used like 0.5 grams. Because if we used 100 grams, not only would you have to fill up your burette more than once, we'd probably have to have the stockroom make more sodium hydroxide. Okay, let's go ahead and look at problem 21 just real quick. It's another stoichiometry problem. And again, these stoichiometry problems, part of the reason we spend a week on writing chemical reactions, predicting products, and getting net equations, net ionic equations, is because you can't do stoichiometry if you don't have a balanced chemical equation. So, this one we've got, you said sulfuric acid?
Yeah, sulfuric
So
acid.
also notice we need nomenclature again. We need to be able to know that, whoa, that's not what I meant to write. H2SO4. Sulfuric acid, and it's reacting with sodium hydroxide?
Yeah.
I'm going to assume that's also in the aqueous state, and again, I didn't give myself enough space. That's going to go to Na2SO4 plus H2. Oh, 2 there, and we're balanced. Right, so being able to predict this is also aqueous, this is also liquid. Being able to predict this becomes a really important aspect, and I'm not actually balanced yet. I also need a 2 there to actually balance it. So, that is how we do that. After we have that, it's really, if you notice,
Wait, are you balanced?
I think I'm balanced. 2 sodiums, a sulfate, 2 hydroxides with 2 H's makes 2 waters. So, one of the tricks to balancing acid-base reactions, if you write H2O as HOH, right? 2 hydroxides, 2 hydrogens.
Oh, I thought the O had I thought there was 8 over here and 6. Okay, I don't know if I looked at it wrong. Oh yeah.
Yeah, so another trick to balancing chemical equations is you can leave your common polyatomic ions as one unit, right?
Mhm.
So it's almost easier to balance this if I call it H2 sulfate plus Na hydroxide goes to Na2 sulfate. As long as my functional group stays the same, I can just balance the whole sulfate. I don't have to think about every single oxygen, every single sulfur. And then plus H. And then water is just a hydrogen with a hydroxide.
Got it.
Sorry.
Yeah.
Is that chair serving a purpose?
No. Would you like it?
Yes.
You're welcome. Do I need to continue on this problem, or is it just writing and balancing the equation? Okay. Then it's just stoichiometry. And honestly, it's almost exactly the same problem we did before, except for now we actually want to go through and do the whole table, find out how much we have excess, identify and eliminate the reactant. This was problem 21. Other problems that we want to look at. Yeah.
Can you do 13?
Sure. What is problem 13?
Menthol, the organic compound that gives cough drops their distinctive smell, is composed of carbon, oxygen, and hydrogen. When 0.1595 grams of
How many grams?
0.1595 grams of menthol is burned in excess oxygen, 0.449 grams of carbon dioxide is collected, 0.184 grams of H2O is collected. What is the empirical formula? And with a molecular weight of 156.3 grams per mole, what is the molecular formula?
Combustion analysis. I didn't actually do a combustion analysis problem in class because you all did so well in the prep activities. I was planning on doing it, but then all of you did well in the prep activities, so I didn't bother because you all figured it out. But let's go ahead and look at how we deal with this. We know we've got a mix of carbon, oxygen, and hydrogen. So the way we can write this down is CXHYOZ. Number 13, sorry about that. Number 13. CXHYOZ goes to, if we're doing perfect combustion, we're going to go to all CO2 gas, and we're going to go to all H2O gas. Right? So this gives us some important connectivity, right? I know that all of my carbon in my menthol, oh, I've also got to have my plus O2. Gas. Menthol, I think, is a liquid, but it really doesn't matter. We'll probably volatilize it before we burn it. Yeah?
Sorry, just a quick question. On the top part, are you saying that COH is that 0.1595 grams?
Sorry, let's CX. Right, I was just keeping track of the things he was reading. Right, and I don't know how many oxygens, hydrogens, and carbons are in there, but I know the sample was that much. I was writing quickly while he was reading. So I know that all of my carbon becomes CO2. I know that all of my hydrogen becomes the hydrogens in H2O. This allows me to set up this situation where I can take 0.449. Why do I keep doing that? 9 grams CO2. That was 1 mole CO2 per 1632, 44?
44.01. Yeah.
44 grams CO2. And then I can also recognize the fact that I've got 1 carbon. Let's make sure we get our units right. 1 mole carbon for every 1 mole CO2. That will give me the amount of carbon. And the only source I have for carbon is the menthol I'm burning. So that's going to be the number of moles of carbon in the menthol. I can do the same thing with water, 0.189 grams H2O times 1 mole H2O per 18 grams H2O times 2 moles hydrogen for every 1 mole H2O. Notice we've got a 2-to-1 ratio in this case because there's 2 hydrogens in every water. And that will give me my moles of hydrogen. Now I can do those two pretty easily because I've only got one source of carbon and one source of hydrogen. The oxygen becomes a little bit more difficult because I've got 2 sources of oxygen. Yeah.
Could you just find out how much, like, from the because now you have moles of carbon and moles of hydrogen? Can you just convert those to grams and then subtract from?
That's exactly what we're going to do. Yeah, so that's exactly the right thing to do. I need some help calculating these things, though.
Yeah.
144 divided by, this is like 0.1. Is that like 0.11? No. 0.01? No, can't do that in my head.
Oh, for which one?
The first one.
Oh, that one's like 0.0008.
Wait,
It's like really small.
no, that was 0.01.
Yeah.
0.01.
Yeah.
0.01 what?
Moles.
No, I mean like there's
Oh.
another digit there. Remember,
0,
these
2.
problems are very rounding sensitive.
Oh, okay.
So we do want to keep
This is 0. Wait, this side. 0, 2.
0102?
Mhm.
Okay.
Oh, that's what. Oh, you were doing moles. Sorry, I
Yeah.
was doing grams. That's why I was converting it into grams.
That's moles. We can convert this to grams by multiplying by 12. 0.0102 times 12. So I think
12245.
so we're going to get 0.122 grams of carbon. We can do the same thing with our hydrogen. 0.189 divided by 18 is again about 0.01 times 2 is about 0.02. So I'm going to go with 0.0204 moles, assuming I can do math in my head.
Is that times 2? No, times 2.
Yes.
Yeah?
So, 18.
Yeah. That's
Wow. I lucked out because it was 0.189 divided by 18.
0.021.
21. Ah.
Close.
0.021, that's after multiplying by 2. Great.
Yep.
Then we're going to go ahead and multiply this by the molecular weight of hydrogen. This is times 12 grams per mole. This is times 1 gram per mole. I can multiply by 1 in my head, 0.021 grams. Now, I can make this realization that my 0.1595 is equal to grams of carbon plus grams of hydrogen plus grams of oxygen, right? Because that mass has to be made from these 3 things alone. And I've got my 0.122 plus my 0.021 plus my grams of oxygen. I'm going to solve for my grams of oxygen. Someone help me. 0.1595 minus 0.122 minus 0.021 is equal to
0.0165.
0.0165 grams oxygen. Go ahead, divide that by 16 grams per moles per gram, and we're going to get about 0.001.
0.0010.
0.00103 moles oxygen. Now comes the last part. So we've got the moles of oxygen, the moles of carbon, the moles of hydrogen. So I can look at this and I can say my carbon has 0.0102. My hydrogen has 0.021. My oxygen has 0.00103. Really? 0.00? Yep, 0.00. Yep. Okay. Assuming we did everything correctly at this point, we're almost done. Now, clearly I can't have fractions of moles in my molecular formula or my empirical formula. So I'm going to go ahead, I'm going to divide everything by the smallest number, 0.00103, 0.00103, 0.00103, and that will result in my empirical formula being something like
It's 9.9 for C. 9.90 to
9.9. H is going to be like 21.
20.388. Let's go about that.
Oxygen is going to be 1. Now, oh, did you say 388, 20.3?
20.388. Yep.
Ooh.
What with that? I had 10, 20, and 1.
So this is the point where we have to say, how much rounding can we do? Is 20.38 about 20?
Yeah.
Not
No.
really. Remember, 0.3 is approximately 1/3. So I've got 20 and 1/3. And I can't just be like, no, it doesn't exist. I'm going to multiply everything by 3. So I'm going to get, so get rid of that 3/8. So if I multiply C by, if I multiply 9.9 by 3.
I think we rounded earlier in the problem, and that's like changing it.
Yeah.
It could. It
Like,
could.
I think that's like.
But if we got the math this way, this is
Yeah.
what we do. And then we're going to see if this is nonsense in a minute because we can look up menthol.
Yeah.
We're also going to see that we're going to get for our empirical formula something way too big. But let's say this is what we got. Let's keep going with it.
29.7.
29.7. H is going to be 61.
4, yeah. No,
And then 03. At this point, because that 9.9 should probably have another digit, I'm going to go ahead and say that's C30, H61, 03. Ta-da! Notice, we should be able to recognize that this is an impossible answer right away, right? So if I look at this, just my carbons is going to give me an empirical weight. This is my empirical formula. Just my carbons is going to give me an empirical weight above my molecular weight. First thing that tells me I made a mistake. Second thing that tells me I made a mistake. You can't do this on a test. Well, we can just look up menthol, right?
Yeah.
We can look up menthol and we're going to see that this is not the correct formula for menthol. So clearly we made a mistake someplace with our rounding. My guess is our hydrogen rounding is what's throwing us off. Is it actually 0.021?
I think it's 0.0204.